Welcome back to the deep dive. Today we are looking at a document that, on the surface, it looks like a standard syllabus for a certification exam.
Right, the PCED-30-02.
Exactly. But when you actually sit down and read through the source material, it feels less like a test prep guide and, I don't know, more like a survival manual for the modern information age.
I would totally agree with that.
Yeah.
I mean, we are just swimming in data. And this exam, the Certified Entry-Level Data Analyst, it's basically trying to codify the absolute minimum you need to know so you don't get fooled by it.
Right. And we're not just going to, lecture on definitions today. We've got a stack of 10 practice questions from the source material. We're going to tear them apart to see why the answers are what they are.
And maybe more importantly, where people usually mess this stuff up in the real world.
Yes, because looking at the weightings here, nearly 65% of the exam is on actually working with data. So it's clear they don't just want you to memorize vocabulary.
No, and that is such a crucial distinction. In the real world, knowing the definition of a median doesn't help you at all if you don't know when to use it versus, say, a mean. One gives you insight. The other might accidentally cover up a massive problem in your whole business strategy.
That is exactly the kind of nuance I want to get into. The source material, it really outlines a journey. It goes from the raw building blocks of variables through the messy process of cleaning, all the way to analyzing and reporting.
A whole life cycle.
So let's start at the very beginning. Part 1, the building blocks.
Let's do it.
Question 1 asks, which type of variable represents categories that have no intrinsic ordering or ranking? The options are nominal, ordinal, interval, or ratio.
And this is where most people, they nod and say nominal, which is the correct answer, A.
Yeah.
But they miss the trap.
Right, because nominal comes from the word name. So we think of things like red cars versus blue cars. You can't say red is greater than blue. That part's easy. But here is my friction point. In the real world, these names are often numbers, aren't they?
They are, and that is exactly the trap I'm talking about. Think of a database ID or a zip code. So 90210 is a higher number than 1001. But is Beverly Hills greater than New York in a mathematical sense?
Of course not. It's just a label.
Exactly. But if you feed that column into an Excel sheet or a basic algorithm, it will happily let you subtract them. It'll let you calculate the average zip code.
Which would be a number that exists, but it means absolutely nothing.
Precisely. Recognizing a nominal variable isn't just about knowing it's a category. It is about knowing that mathematical operations are meaningless. If you treat it like a ratio variable just because it looks like a number, your entire analysis crashes. You're building on quicksand.
That makes so much sense. It's about knowing when not to do the math. Okay, so
Yeah.
contrast that briefly with ordinal, which was one of the wrong answers.
Ordinal's the middle ground. Just think order. T-shirt sizes, small, medium, large. Large is definitely more than small. There is a rank. But you still can't say that a large is, 2 times a small. You can rank them, but you can't do precise math on the distance between them.
Got it. So nominal is just buckets. Ordinal is like a ladder.
That's a really good way to put it.
Okay, let's move to visualization. Question 2 asks, which chart type is most effective for identifying the distribution of a single continuous variable and highlighting potential outliers?
This is where we separate the data artists from the data analysts.
The options were pie chart, line chart, scatter plot, or box plot. And the winner is D, the box plot. Now, I'll be honest, the box plot is the chart I see people ignore the most.
Oh, absolutely.
They prefer the line chart because it's prettier. Or the pie chart, which is, well, we know how analysts feel about pie chart.
Yeah, friends don't let friends use pie charts for complex data. But the box plot, it isn't there to be pretty. It's there to be rigorous.
Walk us through why it's the answer here.
Okay, so a box plot shows you the interquartile range, that little box in the middle, that represents the middle 50% of your data. Then you have the whiskers extending out to show the expected variance.
And the key part of the question was highlighting potential outliers.
Right. So if a data point sits outside those whiskers, it is visually isolated. It screams, "Look at me. I don't fit the pattern."
Why is that better than, say, a scatter plot?
A scatter plot shows the relationship between two variables. A box plot focuses on the distribution of one. It's your integrity check. Before you run a regression or some complex model, you look at the box plot.
And if you see a dot way out in the stratosphere?
You have to ask, is that a real genius discovery or did someone just type an extra 0?
So the box plot is essentially your early warning system.
It is.
It flags the data that's going to break your model later.
Exactly. It forces you to look at the data points that don't fit the narrative.
Which is the perfect segue to part 2. The reality of data. Because once the box plot shows you that crazy outlier, what do you actually do with it? You still have to calculate an average for your report, and that one outlier is going to ruin it.
That brings us to the battle of the metrics.
Question 3. When a dataset contains extreme values that skew the distribution, which measure of central tendency is generally more reliable than the mean? The answer is B, the median.
The classic average home price versus median home price debate.
Break that down for us. Why does the mean fail us here?
So imagine a neighborhood of modest homes, all worth around, say, $200,000. If you take the mean, the average, it reflects that.
Okay. Seems fine so far.
Now imagine a billionaire builds a $50 million compound on the hill.
Suddenly, the mean price of the neighborhood skyrockets. It looks like everyone there is rich.
Exactly. The mean is sensitive. It gets pulled around by the extremes. If you use the mean to decide where to market affordable toothpaste, you'd skip that neighborhood because you think they're all buying luxury goods.
But the median, it doesn't move.
The median is the literal middle value. If you lined up every single house price in order, it ignores the mansion entirely. It just looks at the typical house in the middle of the line.
The source material calls this being resistant.
Yes, it's a robust statistic. When your data is lopsided or skewed, the median tells you the truth about what is typical, whereas the meaning, well, it lies to you because it's trying to account for the billionaire.
Okay, so we use the median to handle outliers. But what if the data isn't just skewed? What if it's just missing? This is question 4.
A huge problem.
What is the process of filling in missing values in a dataset using substituted statistical values called?
The answer here is D, imputation.
Imputation.
Okay.
Now I have to play the skeptic here. This feels a little bit like cheating.
Yeah.
If the data isn't there and we just fill it in, aren't we just making stuff up?
It feels that way, doesn't it? And you should be skeptical. But let's look at the alternative. If you have a spreadsheet with 1,000 rows and 5% of them have a missing value in one column and you just delete those rows,
You're losing data.
you're shrinking your data set. But worse, you might be introducing bias.
How so?
Let's say you're analyzing customer satisfaction. Maybe the people who are really, really unhappy are the ones who refuse to answer the income question.
I see where this is going.
If you delete every single row with the missing income, you are accidentally deleting all your unhappy customers.
Oh, wow. So your analysis would show everyone is happy just because you threw out the incomplete surveys.
Exactly. That is deletion bias. Imputation tries to solve this by statistically estimating what that value likely would have been. We might use the mean of the column or a predictive model.
But there's a risk there too, right? If I just paste the average into all the blank spots, aren't I artificially smoothing out the data?
You absolutely are. That's the danger. It's called variance reduction. You preserve the sample size, which is good, but you trick your model into thinking the data is more consistent, more confident than it really is.
So imputation isn't a magic fix. It's a trade-off. You're trading dilution bias for variance reduction.
Correct. The source material frames it as supporting reliable analytical results, which is true. But as an analyst, you have to know you are manipulating reality to make the math work.
This really highlights why question 7 is so important. It asks, during which phase of the data analysis lifecycle are data formats converted and errors corrected to ensure data quality?
And the answer is B, data cleaning.
The unglamorous hero.
The absolute trenches. The source mentions tasks like improving quality, resolving inconsistencies, and standardizing formats.
Let's talk about that standardizing formats part because that sounds so boring, but it's actually a complete nightmare, isn't it?
It is the single biggest time sink in analytics. Dates are the classic enemy.
Oh, right. Is it month-day-year or day-month-year?
And if you have a global data set, you have both. If you don't catch that in the cleaning phase, your software will read 02/01 as February 1st for half your data and January 2nd for the other half.
And suddenly your sales trends are just completely scrambled.
Completely. And no amount of fancy imputation or median calculation is going to fix that. If you skip the cleaning phase, the janitorial work, the whole building collapses.
So we've cleaned the data, handled the missing bits, and formatted our dates. Now we have to deal with the scale of it all. This moves us to part 3, big data and sampling.
The scale changes everything.
Question 5 covers the V's of big data. It asks, which term describes the speed at which new data is generated, collected, and processed?
And the answer is D, velocity.
Speed equals velocity. Seems straightforward. But is this just a fancy word for we have a lot of data?
No, no. A lot is volume. Velocity is about the flow, and more importantly, it's about the infrastructure you need to handle that flow.
Give me an example.
Think about credit card fraud detection. The system isn't analyzing a static database of transactions from last week. It has to analyze the swipe as it happens.
Right. You need the answer now, not tomorrow morning.
Exactly. Velocity dictates your architecture. You can't use a slow batch processing system if your velocity is high. You need streaming analytics. This source mentions real-time or near real-time analysis. That isn't just a buzzword. It's a requirement that changes how you build your entire system.
So velocity isn't just fast data, it's a demand for fast answers.
Precisely.
But even with fast computers, we usually can't look at every single person or transaction in the entire world. We have to take a sample. Which brings us to question 6. Which method of sampling ensures that every individual member of a population has an equal chance of being selected?
This is the gold standard. The answer is A, simple random sampling.
The other options were convenience, judgmental, and quota sampling. Why is simple random sampling the winner?
It comes down to independence. Because every member has an equal chance of being picked, the sample is mathematically unbiased. You can take that small group and prove that it likely represents the whole big group.
But let me push back again. This sounds great in a textbook, but in the real world, is it actually possible to give everyone an equal chance?
It's incredibly hard. To do it perfectly, you need a sampling frame, which is a complete list of everyone in the population.
Right. If I want to poll all Americans, do I actually have a list of every single American to draw from?
You probably don't. You might have a list of registered voters or people with landlines or people with driver's licenses, but that's not everyone.
So if I just stand outside my office and ask people questions?
That's convenient sampling. It's easy, but it's trash for statistical inference. You're only learning about people who happen to walk past your office.
Simple random sampling is the ideal.
It's the goal we strive for, yes, because it allows for accurate inference, even if perfect randomness is hard to achieve.
Okay, so we strive for randomness to avoid bias. Now we're in the home stretch, part 4. Measuring performance. We've built a model. How do we know if it's any good?
This is the moment of truth.
Question 8. Which performance metric evaluates a classification model by measuring the proportion of actual positive cases that were correctly predicted?
The answer is C, recall.
Now, I always mix this one up with accuracy. Why isn't accuracy the answer?
This is the classic accuracy paradox. Accuracy is just, how many did I get right in total? But recall asks a different question. It asks, of all the people who actually have the condition, how many did my model find?
And the source material mentions significant consequences for failing to detect positive cases.
Yes, think about a medical test for a rare disease. Let's say only 1 person in 100 has it. If I build a model that just says nobody has it, I will be right 99 times out of 100.
So your accuracy is 99%. That sounds amazing.
It sounds amazing, but your recall is 0%. You missed the 1 person who needed help, you killed the patient, but hey, you got 99% accuracy.
That's terrifying.
That is why we need recall. In scenarios like cancer detection or fraud detection, we care much more about catching the positive cases than we do about overall accuracy. We would rather accidentally flag a healthy person, a false positive, than miss a sick person.
So recall is the metric for when you absolutely cannot afford to be wrong by doing nothing.
Exactly.
Okay, question 9. 9 measures error in a different way. Which statistical metric measures the average magnitude of errors in a set of predictions without considering their direction?
The answer is A, mean absolute error, or MAE.
Without considering their direction. That's the key phrase. Why does that matter?
Because in prediction, being high and being low are both bad. If I predict you'll sell 100 units and you sell 90, I was off by 10. If you sell 110, I was also off by 10.
Right.
If I just averaged the raw numbers, so minus 10 and plus 10, they would cancel each other out to 0. And I might tell my boss, look, on average, my error is 0.
When actually you were wrong every single time.
Exactly. MAE takes the absolute value. It strips the negative sign, so we see the magnitude of the mistake. It tells you, on average, you are off by 10 units. It keeps you honest.
Honest metrics. I like that. Okay, finally, question 10. We're looking at relationships. If the Pearson correlation coefficient between 2 variables is exactly 1, what does this indicate?
And the answer is C, a perfect, positive, linear relationship.
The source clarifies. Changes in one variable are consistently associated with proportional changes in the other.
The load-bearing word there is linear.
Why do you emphasize that?
Because Pearson only checks for straight lines. If variable A goes up, variable B goes up in lockstep. But you could have a really strong relationship that isn't a straight line.
Like a curve.
Exactly. Think of stress and performance. A little bit of stress increases performance, but too much stress crashes performance. That's a curve.
So Pearson might look at that and say zero correlation because it's not a straight line.
Right. So a 1.0 means a very specific thing. A perfect straight line lockstep. It's a very strong signal, but it has a blind spot for complex shapes.
So let's wrap this up. Thanks for listening to this deep dive into the PCED 30-02. Good luck with your studies or just with your curiosity.
Keep questioning the data.
See you next time.